query optimizer can perform optimization on logical or physical query plans. The logical query plan can be optimized, or as we call it, rewritten by applying algebraic laws. These algebraic laws, as we have seen in the first part of the query processing discussions, are basically relational algebraic equivalences. Applying them can be an array expression that provide the equivalent of the same expression that has an estimated lower cost. Trivial equivalences, commutative and associative laws, push laws, split laws, and grouping operators are among those we discussed. These laws are applied through rules that are trying to reduce the size of intermediate relations produced in the path toward final query evaluation. After we rewrite the logical query plan, we need to come up with the physical query plan. In this step, estimating the cost of the most effective operator to choose and an estimate of size of intermediate relations are the important factors. In cost-based enumeration, we decide on the algorithms for each operator in the logical plan. For example, using hash join or nested loop join. Why is that important? To answer this, it might be helpful to take a look back on the difference of the cost estimates for different algorithms for an operation. For example, the nested loop join and hash join. So, whenever possible, we basically try to avoid the costly operation and choose the one that optimizes the cost. This depends on the query, the involved relations, the attributes, the operations, and the expression evaluation algorithm used. These are decided in the optimizer and during plan enumeration. The order of joins, as we will see in applying heuristics, or need of additional operators not explicitly present in the logical plan, as well as argument passing as we discussed in materialization or pipelining, are decisions made in the optimizer. Another piece of information we need in query optimization is the size of intermediate relations. In the first part of query processing discussions, we learned using parameters such as BR, TR, and VR and A to find estimate of intermediate relations. These parameters are used to represent a number of blocks needed for relation R, the number of tuples in relation R, and the number of distinct values in relation R for attribute A, respectively. We reviewed possible estimations for selections, joins, and set operations. It is also worth to note a few reduction factors that could be used in estimating the size of operations in where conditions. Reduction factor is the ratio of the expected result size to the input size, considering only the selection represented by the term. The actual size of the result can be estimated as the maximum size times the product of the reduction factors for the terms in the where clause. The reduction factors are calculated based on statistics. For a condition term that has the form column equal value, if there is an index I on this column for the relation, the reduction factor can be approximated by 1 over number of keys in I. This formula assumes uniform distribution among index key values. If no such index is available, the database management system uses a reduction factor based on statistics. For example, system R, used as a reference here, uses 1 over 10 in this case. For a condition term of column 1 equal column 2 form, if there's an index I1 on column 1, an index I2 for column 2, the reduction factor can be approximated by 1 over the maximum of number of keys in I1 and number of keys in I2. This formula also assumes uniform distribution among index key values. Again, if no such indexes are available, reduction factor of 1 over 10 can be used. For a condition term in the form of column greater than a value, if an index I is available, the reduction factor can be approximated by the high value of index minus the value over higher value of the index minus its low value. If no index is available, a fraction less than half, statistically chosen as 1/3, could be applied.